Um, did you see anything?
Yes, yes.
What did you see?
Nothing.
Nothing. Paint. Okay, let's get an example. So we have, I have so many now already. Let's continue from the other day. Let's go back to basic one more time. Cascade control. So this is what we did last time, I guess. Let me check what we have done. Always. Okay, so this is what we did last time. So we have we are measuring the level, and then from this level measurement we are going to send what the measurement is. So we have the y variable over here, and then the set point. So we would like to have, for example, 50% of the level, and then from this 50% and then the measured level over here, we can calculate the error, and this error is then coming out of here. So this error is going to be then sent to the flow controller. It will then say, with this error, you can either you need to increase or reduce some amount of flow rate. So that becomes the set point to this flow control valve. And this new set point is then going to be compared with the measured flow readings over here. So from this line, it measures as well a flow rate, and this flow rate is going to be compared with the set point calculated by the level control. So we have an error as well. So this error is going to be used to open or close the valve. So that's basically this cascade. So we have one level. So we have set point and then the measured variable, and the result is going to be used for set point for another variable. Yeah. So this flow control is basically controlled by this level control. So this guy over here, this loop, is what we call as a slave control, slave. And while this guy, this loop, this bigger loop, is what we call as the master control, because it is then being the master for this controller, means it gives the set point for this controller. So that's basically what it is. In terms of the yeah, for control, yeah, I think I can suggest to you for you this website, controlguru.com, because I also refer to this website every now and then, just to get a refreshment or to get some yeah, more knowledge or input. So this control guru, you can Google this. So in terms of the I don't know if you still remember this uh, uh, this block diagram basically. So if you can, then I will put this side by side, yeah, so that you can how do I do this? I can put this side by side and put it there. Where is that thing again? Yeah, now you can see both. Yeah, can you see both?
Yep.
Now so we have this set point. So mathematically, that set point, this set point, the one we want to have, yeah, this is the level that we would like to see. So this is then this primary or outer set point. So this one SP1, so this is set point 1. People call this like a primary control or master control, whatever you would like to call it. Yeah, so this set point, so we have that set point, and we have this y variable, which is then the level that we want to see. So this y variable is coming from this line. Yeah, so this is basically the level that we are going to see. This is what we want to see. So if we want to, for example, 50%, so if this is then 50%, this signal will come back to this block, and it will then calculate the error. And then it gives the, and it will then calculate the error over here, which is somewhere here inside. And then it gives then the outlet is then the what is then the required flow rate in this particular case. So what is then coming out here is then the required flow rate. So this required flow rate becomes the set point for this control. So again, this is the same. This is the can you see my cursor moving? Yeah.
Yes, yes.
Okay. So this is then going to be the set point, coming from the primary control, and this set point is then going to be compared with the flow rate measured here, the variable from this inner circle, so which is this inner circle. So the variable that we want to see is then the flow rate. So this flow rate we measure, and then we compare it with the set point coming from the master control. So we measure the flow rate, and this flow rate is then being compared to the set point coming from the primary control or the master control. So that gets we have another error, and this error is then sent to the to control. The logic behind it, it will then say, okay, you need to either to increase or to open or close the valve, so in this case it will then say it will open or close the valve. And then it will then, if it's closed, and then it will then be closed, and then we have a lower flow rate over here, right? This lower flow rate over here, so it's going to be like a lower flow rate over here. And then if it's the lower flow rate over here, that means the level will then go up. So lower flow rate over here, and then it goes to this level tank, and then this level will then go up. So if this level go up, it will then send back to here, so that it can be compared further whether this level is okay or not. Yeah, so this loop is basically the inner loop or the secondary control, or the slave control, you can say that. This one is then the master control or the primary control, like in this case. So we have the small loop and the bigger loop. Okay. From here, is there any question?
Are there cases where the cascade structure is more complex than one master and one slave?
No.
Maybe.
No. This is then the as complicated as it can be for the cascade. It's very rare to have more cascade in a cascade. I have never seen that. Yeah, I've never seen that. This is then the common cascade control that we can see in the field as well. So we have only like one loop, and then the outer loop. So slave control, and then the master control.
Okay.
Yeah, and in this case, you might wonder, why did I not explain about this part? So this part is like basically the disturbance into the system. So this is what we call like this feed, because this feed flow rate is just like it goes up and down according to whatever it wants it to be, right? Because we don't have any control over here. So if the flow is if the flow coming is then smaller, lower, that means that the level can drop. So this level can drop because of this smaller flow rate. Or if the flow rate is high, that means the level can go up. If the flow rate over here can go is higher, and then this level over here can go up. So this is then this fluctuations in the feed is then an example of this disturbance, something that we cannot control, something that we cannot measure, as well as we cannot control. This is typically for the level and flow rate control. There's also a thing called like this one. The same goes with this one. This is what we know as like a temperature, for example. So this temperature, so we have a steam coming in, and this steam is then heating up the water in the tank, and then it measure the steam outlet temperature. So this steam outlet temperature is what is coming over there. So this steam outlet temperature is then going to be then to open and close the valve. So this outlet temperature, the steam outlet temperature is going to be used to open and close the valve. Yeah, so this is then the inner circle, and then it has the set point from here coming from this controller. Yeah, so you can see the arrow coming in. So this controller is then measuring the outlet temperature here. So it's measuring the outlet temperature over here. So it gives the signal back. So we have the temperature going down, for example. If the temperature goes down, it sends the signal back to this guy, and it wants to see a temperature increase because it's going down. Yeah, and then it gives then the set points for the steam to come. So we need to have more steam, it says over here. So it will give the set point over here. So temperature drops, so we need to have more steam. So it will then compare this steam with the current steam flow rate. Yeah, it will then compare the steam over here to the current steam over there. If they say we need to have more steam, that means we need to increase the steam flow rate. When to increase the steam flow rate, that means it will then have to open the valve, so then the steam will then flow through the system. So it will then let the steam flow through the system. So we have higher flow rate over here of the steam in this circle. So this is then a slave control. This is the master control. Any questions on this one? And then again in here, if you can see, I forgot to mention, so this disturbance can be the temperature of the water inflow, or maybe both temperature as well as the flow rate, because if you have a higher flow rate and a lower temperature, we have a multiply effect of yeah, being this disturbance of the temperature over here. Well, yeah, that's typically it. So we have another example. So we have so this temperature, it measures the so this reactor, its temperature is then measured. So it measures the still of the temperature of the reactor. So it gives then it measures the temperature, and then it compare with the set points of the temperature, and then this becomes the new set points for the flow of the steam to come into the system. Yeah, so this is then the slave control. Yeah, and this is then the master control. The easiest thing is then to see, okay, so where is this set point coming from? So this set point coming from the measurements over there, and then where is the set point of this guy coming from? This set point of this, the set point for this is coming from another set of controller. So that means this is going to be the slave of this controller. So if this is then the slave of this controller, that means this is then the master of this controller. So hence we can see that this is a cascade control or master slave control. The same goes with this. We measure the temperature here, and then if it's not suitable, and then we can then calculate the new set point for the flow rate of the steam or the coolant in this case. So this is then the slave part, and then this is then the master part. I think that's enough here. Because the rest is more or less the same. So what we did last time, so see, you can see as well, this is then the slave. I put here a slave because it's a small loop over here, and then this is then the master control. It has a bigger loop. We could also do, I think, in this case, let's do it this way. We are going to make another. We're going to hit this flow rate. Hit this stream. Yeah, what's the temperature of the stream? 30 degrees C. So we can hit that. Active, and then the flow sheet model. Let's see, we want to hit it up. Oh, we are running it. Stop now. And then we are going to connect this stream into this guy, and then from this guy to another stream, and then we have the energy stream. Yeah, so this is then the energy stream. Horizontal. So we can either have In this case, yeah, in this case we can have like a straight control. For example, we measure the temperature over here, and then we will then control the flow rate or the duty of the heater. So in that way, it's like a single loop control. We could do so. I think later on we could also do the if we have like a real heat exchanger, yeah. But for that, I think we need to have like a good case, because we need to have the volume and details of the heat exchanger. But in this particular case, because you want to make it quick, I'll just show you how to do the temperature control, for example. Yeah, so we would like to see, so in this case, for example, we would like to because we are going to manipulate this flow rate, we're going to manipulate this duty in such a way that temperature goes up and down. So in this particular case, we will use this as the variable to adjust. So say for example you want to increase the the you have like I don't know, yeah, maybe heat flow is 10. Let's see what happens. 10 kilocalorie per hour, or maybe a kilocalorie. Let's use the unit that we are that we know. So 1000, maybe 1 megawatt is 1000 watt. Is this happening or no? Not really sure. Because I don't remember the notations, whether this is going to be positive or negative. Anybody can remember? Um, yeah, because we would like to increase this temperature. So we need to understand the notations for the positive and negative. Let's see if I increase it, because we are not running this, but in any case, um, if I remove this, so to say, and then say for example 20 degrees C. Oh, it's not running, yeah. Yeah, no, we know. Nonetheless, let's do it this way. Let's just continue. We'll just see, along the way we'll just see whether what we are doing is correct or not. Come on. Okay, and then for dynamic we have to see the dynamic type, and then we would like to have what do you want to how do we want to do the calculations? Are we going to supply the duty, or the duty fluid, or the product temperature spec? In this case, because we are going to want to vary this, so we just say we supply the duty. And then the volume, so in this case, yeah, you can specify the volume yourself, and then you can either make it 2.1 or maybe one cubic meter, depending on the size of the heat exchanger. And then for the other one, yeah, because we have already the volume, and then we need to know the resistance in the heat exchanger. So in this particular case, we can either calculate K means here the resistance. So if you see the valve is then there is a CV of the valve. So in heat exchanger, that CV is then defined by the K over here. So the higher the K, that means the easier for this to flow through the heat exchanger, or the lower the pressure drop. But then the other way around, the smaller the K, that means the higher the pressure drop, as well as the less easier for the flow to flow through this heat exchanger. So you can calculate K. Seems to be added now. So you can just tick on this. Yeah, you can tick on that. Otherwise, you can always ask later the dynamic assistant. Yeah, So that's one. So we specify this. Okay, click here. I don't know. And then we click, and then this one is done now. Becomes, I don't know if you can still remember the dynamic. In the dynamic simulations, we work based on the how do you call it, the boundary. So we have a boundary. So we have a boundary, and then we have incoming stream, and we have outgoing stream, and then this outgoing stream is then a valve. There's a valve over here. So in this stream, we specify the pressure, and then in this stream as well we specify the pressure. Okay, so in common process simulation software, we can replace this valve with a heat exchanger, yeah, as long as there is a flow restriction, because because this guy basically it has a flow restriction, yeah, where the flow is then as a function of delta p, the valve as well, so it's a flow as a function of delta p. But the heat exchanger as well, in most in I think in, I don't know if it's in all, but in most process simulation software, it has this k, which is also going to be used in the f as a function of delta p, and then that delta p is then a function of k. Okay, so in this particular case, we don't need to add a valve. You can if you want to, but not necessarily. If we have already the heat exchanger, we'll show you. But then in this case, in this particular case, we need to specify the pressure here. Okay. uh, in our now we extend the border, yeah, we extending the border of the simulations. It was this, but now we include the heat exchanger into the system. So that means when it was this, when the boundary is this guy, in this size, this stream 5, we set the pressure, its pressure as the boundary. So in this particular case, because we extend the boundary, so that means this is no longer active. It is no longer active. What we need to make active is this, the pressure. So this pressure, we can make it active, and this you can make like, I don't know, a 3 or 5, 4, maybe 4.5, yeah, just to see. If we want to specify half a bar to the heat exchanger, so we can make like a 4.5, for example. So and then we add a controller. Oh, we don't need to add controller first. We just see if it runs, yeah, and then see what the temperature is. So in this particular case, we can also do show table, and then we'll see. You can see temperature and the flow rate. So I don't want to have molar flow rate. I want to have mass flow rate. Yeah. In this case, we do save as, just in case that this simulation go haywire. 1203. Okay. So if we think we have done everything, we can always go back to this dynamic and then see the dynamic assistance. So this dynamic assistance doesn't say, oh, it doesn't identify any problem, so we are okay. Click analyze again, and we are okay. Otherwise, if we say, for example, you forgot to deactivate this, for example, you forgot to deactivate this, and then we think that we have done everything right, and then we can go to this dynamic assistance, and it says, yeah, there's something that you have to do. So disable stream pressure specification. So we can double click on that, and then it says stream number 5. So number 5, we need to remove pressure specification in this stream. So this, then we can either make change over here, we can click it here, or we can just do it manually from here. So we can just do it from here. So when we click it, green, and then that tick is no longer there. Okay. And then we can just click run integrator. Integrator is there, so we can, yeah, you can send it back to 0. Yeah, it's up to you, or we can click reset basically. And then we can run it. So now you can see, if we supply 1 megawatt, it's 800 degrees C. That doesn't make any sense. So we supply like not 1 megawatt, but 100, maybe 10 kilowatts. 10 kilowatts. 10 kilowatt, it goes to yeah, somewhere around here. So 10 kilowatt is also very big. So make it like maybe 1 kilowatt. I did 1 kilowatt or no? Nah, no, it's stable already. Oh, we forgot to put the chart. Yeah. Okay. So there's a spike over here and there. This is then, I don't remember what we did last time. So red is then FCV. Okay. Green is then PCV, and okay. So you can see now here, this red, this flow control valve, it's how do you call it? It's fluctuating very strongly, and we can see the flow rates also fluctuating very strongly. So this is a sign of an unstable control. Yeah, this is a sign of unstable control. Also, one way to reduce this is then, if we see that it is prolonged like this, it's not stable, but now it's getting better also. Yeah, so I see it's not stable, it goes up back, and this unstable control situation can be either can be of several things, but then the most common ones, we have the controller is too aggressive. Like I think you understand. So if you can see this behavior, it may crash the simulation. But it's just to give you an idea. Yeah. Either the controller is too aggressive, either that means we either make the KC too high or the tau I too small, or the valve is too big. Okay, so these two situations. So we can then now see, because this is FCV. Yeah. So this FCV, so we have the controller as well. So see, it goes up and down. The size of the valve, what's this in the size of, we did size this, right? I mean, we did size this using the rating. So I'm not really I don't think the size is then going to be a problem, because we size it based on the flow rate on our steady state simulation, so that's not a problem. So another issue is then it could be that because the control is too aggressive. So if we can then make this into 1/3 of that or half of that, yeah, depending on the control tuning that we follow. So let's make it a half. And see what happens. To plug in my laptop. This is mass flow is red. Yeah, so the flow rate is so it's okay. So we can make it like less aggressive. Is there any questions so far? In the meantime, we can, while waiting for this, so we can see the fluctuations reduced a little bit. We can go to this control guru, yeah, control guru. PID controller. There's also design and tuning. You can see. I would like to see the effect of KC. Maybe there is KC somewhere. This one. Can you see? So this, they say it's the proportional term is here KP, but it's also KC. Yeah, whatever you want to call it. Yeah, it's we need to make sure it's a proportional controller. So if we increase the KP, if we increase the KC, so this is divided by 2. That means make it smaller. It has this kind of performance. But then if we double the KC, you can see it's the response is faster, right? So it's not that sluggish, but it's a faster response over here. But it gives us these oscillations. But then if we multiply by 2, so we increase the KC even further, so it gives us these oscillations. So this is what is happening in our case. Hence I did reduce the KC from these situations to hopefully into these situations. The same goes with the tau I. So if we have the tau I, if you have a smaller, if we make it a big tau I, because this tau I is on the denominator, yeah, in the denominator. So if we make it this big, that means the effect of I controller is then smaller. And if we then make the tau I smaller, that means we can have the effect of the I controller bigger. So you can see from here to there, it becomes more aggressive. From here to there becomes more aggressive and more aggressive until it oscillates. So that is what's happening for the KC and tau I. And this one we can even reduce it further. So from this onwards, it's just a matter of applying the knowledge of the control that we have to various different situations. The concept is still the same. The way we do it is still the same. Yeah. So The way we do it is still the same, and the way we build the simulation model is still the same. So we need to define the boundary, and then uh, um, uh, outside of the boundary we need to define the pressure, the source, either the source over here or the sinks over here and there, and then we have to size all of the equipments around this, and then and then do the controller, yeah, and that's it. So it doesn't it's not that what you could see as well here, because we just did the we just how do you call it, we did not have any size of the heat exchanger, so we just size it yeah, to whatever we want. And then you can see the with this K, the pressure drop goes up and down very fluctuatively, so that creates the fluctuations in the system, as you can see now here. So we have reduced the Kc of the flow controller, but it's still there, it's oscillating a lot, yeah. So we can be suspicious that this could be because of the new equipment that we put in, right? So can you follow the logic? And then when we click here, we can see that up and down. So in this case, maybe we want to yeah, maybe reduce the or the increase the K a little bit to dampen this oscillation. Make it 20.
So what is K again? How does it I mean, how does it affect the flow?
Um, we specify pressure here, yeah, and then there is a K value here. So depending on the pressure over here, and then it will then calculate for us what is then the required pressure here. You follow? Yeah, because we specify pressure. This one, it has the pressure flow relationship, and then it will then calculate the flow rate over here and then the pressure here. And then if this pressure is then depending on the flow rate, it can go up and down as well. And then this controller will then behave going up and down as well, because it needs to maintain the level in the tank, yeah. Because if this goes up and down, this goes up and down, this goes up and down, it will then affect the going up and down of this valve as well, as we have been seeing so far, yeah. So if this level goes up and down, that means the space for the vapor will then go up and down. It will then create the pressure going up and down, and so on and so forth. So if one of the system is not stable, so in this system, if one of the equipment is not stable, that instability, it can lead to instabilities in the other places, as we seeing now here.
Okay.
Yeah, this we just well, the correct way to do this dynamic simulation is then to get the size correctly, yeah. So in our case, we start this simulation from the steady state, where we can then utilize the sizing rule of Aspen-Heises. There is a sizing, but when we add this, we did not start from the steady state. So we started directly from the dynamic, and so you saw that when I click calculate K, it doesn't calculate anything, yeah, because it doesn't it's not being calculated in the dynamic mode. So it will be calculated in a steady state, but since we did not do it correctly, so we get this oscillation. You could see maybe if I want to increase this a little bit further, 50, I don't know, I'm just playing around with numbers. So this is just a matter of playing with the numbers here. There's not rocket science or whatnot. So it's just if you find the same situations in when you do your simulation later on. So the best way to go is then to check whether the size that we have inputted correct or not, and then to see on the field whether the system that being modeled is correct or not. Means if have you modeled this in accordance with the with what is happening on the field or not. Um, uh, Try to get information as accurate as possible, as much as possible, and then you can make a nice simulation. The green one is PCV. I think PCV is also very aggressive. Maybe we can make it like it's gonna be 10. Yeah. Now the system is yeah, more a little bit under control. I haven't utilized this auto tuner. Yeah, I don't know. Yeah, I haven't done so. So you could I think for your exercise, for your own benefit, you could um, find the document in the help and then see what these options are doing, because I haven't done anything on the advanced levels of this control. I just use this first page. The rest I haven't tried them. And then if you have done so, and then let me know next week, because I need to learn from you as well. Where's the thing? Make it less. Maybe we can reduce this pressure a little bit. 4. So basically, this is when, yeah, basically what we do to solve the controller issue in the system. Do you have any questions on this part? Yeah, we just need to check the controllers and then the size of the equipment, and the valve as well. The size of the valve. If the valve is too big, it's also lead to uncontrolled or unstable situation as well. And then for the remaining, it's just like the repetition of this yeah, calculations, or the way that we do the simulation. Is just its repetition. Any question?
I do have a question about exchange there.
Uh-huh.
So when we were running dynamic simulation just now,
Mm-hmm.
the the duty supplied is, how would I say, it was controlled by the.
Duty is not controlled by anything.
So how does it? How does the temperature change again?
Yeah, temperature changes because we specify. We put in
pressure.
1 kilowatt. Yeah, so we
Mhm.
put in 1 kilowatt, and then if we have a higher flow, that means this temperature will drop. If we have a lower flow, that means this temperature will go up. Yeah, it's MCP delta T.
Alright. Okay, so we are. So in a case where we want to control the temperature,
Yeah, you
how
can
would
do
that
so.
be?
You can do so. The same like in this flow pressure level and then flow rate. So we need to so we can say
Or is this exchanger here is used to control the pressure?
no. Exchanger is not used to control pressure. Hey, what is happening in my mind? So we put a PID here,
Mm-hmm.
and then we can name it like a temperature control. So what do we want to control? We want to control the temperature in this stream number 7 to be temperature of stream number 7, right? So temperature all the way down, temperature of stream number 7. Click select, and then
Because as of now, I don't really get the purpose of having exchanger there.
no, it's just to play around, Aisha.
Okay. Alright.
So I just because we have already the flow control, pressure control, level control, and then why not as well have the temperature control. So to be able to control temperature, that means we need to have an heat exchanger. As simple as that. Yeah. So how do we then control this? We are going to do this guy control valve and then select, right? So this control valve needs to be because this is a bit different, so we have to go to the control valve because it says here control valve is not set. Means this control valve means we have to set the flow rate here. Infinite. Now is what is it now? 800 kilocalorie per hour. 800. Let's make it 2000 or 5000. Right, and then so we specify sorry, minimum is always 0, and then the maximum is this. We have specified the maximum, and then it's a direct queue, yeah, not utility fluid, because we are not modeling any utility fluid at the moment. And then the control valve has been sized, so there is no other comment on that. And then it says here PV, so PV is then the PV. So make it not so aggressive. PV is then the process variable that we want to measure. So we can make it either 30 degrees C or something, maybe minimum like, I don't know, maybe 20. We can just put it a range where the value that we want to have is in between the range. So in this particular case, we can make it like make it 100. It's automatic. So not a degree C, make it like 40 degrees C. Now I don't remember. It's going to be positive or negative. Seems to have an increase in temperature if it's positive, right? So that means if we increase it further, temperature will increase. So if temperature increase, then if the temperature is higher than the set point, that means we have to reduce this. If temperature drops than the set point, that means we have to increase this. So it's a reverse exactly. So reverse auto 40 degrees C, blah blah blah, and then we can make it active, dynamic. Oh, it started already. So the opening, the valve is increasing, means it's giving us the see, the flow rate, the duty is going up, temperature goes up, hopefully, and then it will then yeah, because we have a fluctuating flow rate here. Flow rate is not that constant. Hence, even though we increase the operating variable, temperature may not increase proportionally. Yeah, we need to solve this flow variable, the inconsistency, the instability of the flow beforehand. I think looking at the timing, we will try to solve this instability of the system next week. I will just let you think on how to do this, yeah, or you can do it on your own, and then let me know next week.
Okay.
Yeah, it increases slowly, so you can make it faster as well if you want. Let's double this, make it more aggressive. It's temperature control anyway. Okay, let's stop this here, and then save it. And we will see what we can do next. Yeah, I think in terms of for me, from my side, in terms of making steady state simulation, we have done so. Yes, you need more practice to do so. Developing dynamic simulations, we have done so, and then defining the control variables, we have done it. And indeed, you will need more practice to be able to make this on your own. What do you propose next week? Shall we then yeah, try to do whatever we want over here, or we can try different case on steady state, or different case on dynamic, or what you would like to model? And then you can discuss next week here.
Oh,
Okay.
yeah.
Yeah. Again, as I said, again and again, that this is a skill that you have to practice on your own. You will not be able to do simulation just by watching me doing the simulation. So you have to do your own simulation, and then you get stuck, and then you come to me, and then we discuss, and then you solve it, and then you do another case, and then you get stuck again, and then we discuss it again, and then you solve it again and again and again, until you do this like dozens of times, and then you'll build up your skill. Okay. Yeah, make a case study, and then see if you can stuck. Yeah, just make yourself stuck, and then we will discuss on how to solve it. Okay.
Okay. All
Good.
right.
Thank you.
Thank you, doctor.
Yeah, bye bye.